Hello everyone. In this video, we are going to derive integral tan x, integral cot x, integral secant x, and integral cosecant x. Previously, we saw different formulas in the other videos, how from differentiation those formulas has been derived, everything we discussed. Now in this, we are going to use an integration procedure to derive these formulas for tan x, cot x. So let's start with that. The first one which I'm going to derive is going to be integral tan x. So here we have integral tan x dx. How to start this? We don't have any formula for tan x directly. We take a help of sine and cos. That means I'm representing tan x as sine x by cos x dx. Now the next step what we would be doing is substitution. Which one to consider? Obviously, I would be taking in help of my denominator cos x. Cos x is there. I'm going to consider this as t. When I differentiate cos x, I get minus sin x is equal to dt by dx. So minus sin x is there, so it becomes sin x dx is equal to minus dt. Now the problem entirely, I'm changing it. I'm considering this as I is equal to. From variable x, I'm going to change it to variable t. So now here, the question is getting changed. Just observe where you have t, you have it in the denominator. Cos x comes in the denominator. And then sin x dx becomes minus dt. So which is going to be minus ln of mod t after integration plus c. What is your t actually? It is minus ln of cos x plus c, right? So now this can also be written as, so this is going to be integral tan x dx, or this can also be written as integral tan x dx is equal to ln of secant x plus c. We have something like ln of m ln of a is equal to ln of a to the power m. By using this concept, you would be getting 1 by cos. 1 by cos is nothing but secant x. That's how the changes has been done. So this becomes one of the important formula for us. Either this one or the other one we would be using. Now let's go on with the second proof. The second proof is regarding cot. Integral cot x dx. Let's do the proof for this one. I would be obviously taking a help of definition of cot, which is cos x divided by sin x dx. So obviously substitution when it comes, I would take the denominator's help, and when I differentiate sin x, I get cos x dx is equal to dt when I differentiate both the sides with respect to x. Now when I do the changes here, I is equal to dt by t, which is equal to ln of mod t plus c. And what is my t actually? It is sin x plus c. So our formula for integral cot x dx is ln of mod sin x plus c. So I think these two formulas you have learned now. We'll go with the third one. We have third one, which is integral secant x dx. Oh wow. Here, if I go ahead with 1 by cos also, it's not going to work. So I would be doing few changes here. Like I need to introduce something. See here, we have something for differentiation of secant. What is the differentiation of secant? Secant x tan x, that's how we do it, right? And And what about the tan x when we differentiate? We get it as secant square x, right? Now, now what I would be doing, I need to introduce something where when I go with differentiation, I need to introduce something when I go for substituting something, then I would be differentiating it, right? So when I do that, the other part has to be my question itself, the remaining part of the question. So I take an help of multiplying and dividing by secant x plus tan x. Okay. So now here, the I which I'm considering, it gets multiplied with secant x into secant x plus tan x divided by secant x plus tan x dx. Now we will get secant square x and then secant x tan x, right? It solves our problem actually. See here. Now let's go for substitution. Let secant x plus tan x, the denominator which we have, I'm considering it as t. Then when I differentiate this both the sides with respect to x, I get it as secant x. When I differentiate, I get secant x tan x plus secant square x and then into dx is equal to dt. Now if I just take secant x common here, just observe you have that is your numerator tan x plus secant x dx is equal to dt. So now your I is equal to, you have dt divided by t, which is ln of mod t plus c, which is equal to ln of secant x plus tan x plus c is nothing but the integration of secant x dx. It's one of the important formulas like the other two because we would be using these things in problems hereafter under substitution. Now the next one which we have is the last one which I'm going to derive is integral cosecant x dx. In a similar way as I took a help here of secant x plus tan x, I would be taking a help here of cosecant x plus cot x. So I would multiply, I will let me consider as I. I is equal to, I have cosecant x divided by cosecant x plus cot x, and I would multiply here with cosecant x plus cot x and then dx. So we have here cosecant square x plus cosecant x plus cot x, right? Something like this we have. Now here, let me just go ahead with my substitution. I would be considering my denominator, that is cosecant x plus cot x is equal to t. When I differentiate it both the sides, I get for cosecant x, I get cosecant x cot x with a negative sign. So minus cosecant x cot x. And then when I differentiate cot x, I get minus cosecant square x. And then into dx is going to be equal to dt. When I'm differentiating both the sides with respect to x. Now if you observe, if I take minus as well as cosecant x out, I get cot x plus cosecant x. Excluding the negative, the remaining part is my i's numerator is equal to dt. Okay. Now what we would do is I is equal to minus dt divided by t. So minus ln of mod t plus c, which is nothing but minus ln of cosecant x plus cot x plus c. So this is gonna be my integral cosecant x dx is gonna be equal to. So this one is gonna be the fourth derivation. And all these four formulas are very important and we would be using in the problems hereafter. Thank you.